Welcome. In this video tutorial I will illustrate how to integrate EyeLink eye trackers with experiments created using the stimulus presentation software ePrime. There are two ways in which this can be done. You can integrate ePrime with EyeLink systems using the ePrime extension for EyeLink, which is a paid option available for ePrime 3, or via the use of inline scripting to call items from our developers kit, which is free and works for all versions of ePrime. This video describes the second approach. During the tutorial, I will walk through the EyeLink picture task, which is just one of the ePrime templates that we provide. It illustrates the core EyeLink ePrime integration functionality. Other templates illustrate additional, more advanced integration features, including the implementation of gaze contingent tasks. Throughout the video, we will be using ePrime 3, but as mentioned earlier, the same approach will also work with ePrime 2, and we also provide legacy scripts for ePrime 1. Before we run through the script, we will first cover some basic background information about how EyeLinks work, and how the EyeLink Developers Kit is used to handle the ePrime integration. Tracking gaze with EyeLink eye trackers typically requires two computers. The host PC is provided by SR Research and runs our eye tracking software in a real-time operating system. The host software provides an interface to the eye tracker that allows the experimenter to set up the participant, perform calibration and validation, and monitor gaze during data collection. The stimulus or display PC runs the stimulus presentation software, which in this case will be ePrime. Critically, the two computers communicate with each other via an Ethernet link. The display PC can send messages and commands to the host PC, and the host PC sends gaze data to the display PC, allowing gaze contingent tasks to be developed. The link also allows various camera setup operations to be performed using the stimulus PC screen. In order for this communication to work, it is important that you configure the display PC's Ethernet address appropriately. Please see the installation guide for your system or this FAQ on our support forum for further details. The EyeLink Developers Kit provides a set of core libraries written in the C programming language that allow other languages such as Python and stimulus presentation software such as CyclePy, CycToolbox and ePrime to interact with the host PC and control the EyeLink system. The Developers Kit will need to be installed on your display PC. In a typical eye tracking experiment, the Developers Kit libraries allow other software to establish a connection with the host PC, open an EyeLink data file, specify various host PC parameters such as the calibration type and colors, set up the participant and camera, perform calibration and validation, start and stop recording data, send messages to mark critical trial events such as stimulus onset, send data viewer integration messages, and transfer the EDF file to the display PC at the end of the task. Getting started with EyeLink and ePrime integration is very straightforward. There is a very comprehensive post in the Learning Resources section of our support forum that outlines all the steps you need to take, along with some useful links. This thread is linked in the description below. In brief, you will first need to make sure that you have configured the Ethernet settings on your display PC to allow communication between it and the host PC. Typically, this involves setting its address to 100.1.1.2 with a subnet mask of 255.255.255.0. Detailed instructions for all operating systems can be found in the user manual and in this thread on our support forum. Next, make sure you have also installed the latest version of ePrime. Finally, download and install the EyeLink Developers Kit from our support forum. The link is below and in the video description. So let's take a look at the EyeLink picture example. After installing the EyeLink Developers Kit, it can be found in the ePrime subfolder of the EyeLink Sample Experiments folder. You may not have right permissions in this folder, so to run the project, please copy it to somewhere like your Documents folder or desktop first. The EyeLink picture task is a very simple task that presents 4 images of different sizes and for each image records gaze for 8 seconds or until a key is pressed. Most of the code in the script is designed to illustrate the range of EyeLink integration functionality that is possible via ePrime. You may not require all of the components in your own script, but it can be useful to know what is possible. Some task-specific functionality is not shown in this example, but can be found in others. For example, the video example shows how to properly add video playback messages for data viewer integration. The GC Fast Samples example shows how to present a gaze contingent window. Picture MRI focuses on a project run in an fMRI environment, and Fixed Window Fast Samples and Saccade Event show how to access gaze data during the experiment runtime. Like the EyeLink picture task, these other examples are all heavily commented, so if you need to add any of these features to your own project, please take a look at the inline scripts that they contain. Back to the EyeLink picture task. The script illustrates the following integration functions. It establishes a connection with the eye tracker, sets various tracking parameters, opens an EDF file on the host PC, allows the experimenter to perform camera setup and calibration validation. It starts and stops the eye tracker recording for each trial. It sends messages to the EDF that mark critical trial events, sends data viewer integration messages to facilitate subsequent analysis. Finally, it closes the EDF file at the end of the recording and transfers it to the display PC. Before we go through the code itself, let's quickly run the task and take a look at what the participant sees on the display PC screen. Then we'll see what the experimenter sees on the host PC screen, and finally we'll take a quick look at the data in Data Viewer to see how the Data Viewer integration works. After launching the task, the first thing that happens is that you will see the usual ePrime prompts for session name and session ID. Next, we see a notice that gives some advice about screen resolution settings. We can ignore this for now. Next, you'll see a prompt for the EyeLink data file name. I'll leave the default test file name. Pressing any key brings up some basic operator instructions with reminders of the various keyboard shortcuts for performing calibration, validation, and putting the eye tracker in output mode, which will launch the task. Pressing enter allows the camera image to be transferred. Pressing C launches the calibration. As you can see, the calibration targets appear one after the other. Typically this would be followed by a validation, but I've skipped that to keep things short. If the calibration and validation are good, the Enter key is pressed to save the calibration, and then the O key is pressed to switch the host PC into output record mode. This starts the experiment, and a basic welcome screen with instructions is shown. After pressing a key, each trial begins with a central drift check target, followed by an image, which remains on screen for 8 seconds, or until a key press. This sequence is repeated a total of 4 times. The task ends with a brief thank you before returning to ePrime. Now let's take a look at what the experimenter sees on the host PC screen when the task runs. During the calibration, the experimenter sees the targets appear one by one and a representation of the raw pupil-CR data in uncalibrated space. Again, I've skipped the validation to save time. After the participant has read the instruction screen and pressed a key, a drift check target appears, and when the experimenter presses the spacebar or Enter key on the host PC, the trial recording starts. As you can see, the trial image also appears as the backdrop on the host PC recording screen. The host PC also displays a status message that allows the experimenter to keep track of which trial is being run. When the experiment is finished, we can open the EDF file with Data Viewer. In Data Viewer, we can see that the recording has been parsed into 4 separate trials. If we toggle on message visibility, we can also see various messages that are flagging key trial events, such as the onset of the image and the blank screen that ends the trial. These messages can be used to set an interest period. We'll do this by entering the messages into the IP Start Event Settings and IP End Event Settings sections of the Interest Period editor. Having set an interest period, we can click through the trials and see that the relevant image is being shown as the backdrop in the spatial overlay view, and each trial contains an interest area that surrounds the image. Finally, if we open the trial variable value editor, we can see a number of variables and their associated values, including trial number, trial identifier, picture, max duration, and others. So let's take a look at the template itself and see how it works. At the top, we have the first and most critical component of EyeLink integration, the user script. The user script needs to be copied into any ePrime project that requires EyeLink integration. It is the same script in all of our provided examples, so please feel free to copy this into your own project from any of them. You can also add any additional functions that you might require for your project to the user script, but the existing code itself should not be modified. The user script provides support for various critical eye tracking functions, including drawing the calibration and validation targets, allowing the camera image transfer, and properly setting the output file name. It will not be discussed further in this video. The README script simply contains some general information about EyeLink and ePrime integration. Please do take a look. The following important notice slide is just a reminder to set your desktop resolution to the same resolution the project is set to run at. The next critical integration step, placed at the session level, is the EL-Connect inline script. This script handles the initial connection and configuration of the eye tracker via the host PC software, so we'll go through it in some detail. The script starts by setting the values of some useful variables. The first, EL camera setup type, determines whether the host PC camera image can be transferred to the display PC during the camera setup phase. This is usually preferable, so the flag is set to 1. In the past, transferring the camera image could sometimes cause some brief transition delays in ePrime, but this should not be the case for current versions. If delays between camera setup and the rest of your project do occur on your hardware, or if you're using a legacy script that uses the no-cam method, the flag can be set to 2, disabling the camera image transfer functionality. The next 2 flags are set to 0, and for modern versions of Windows, these default settings should be fine. If you're running ePrime on Windows 7, you may find that changing these values to 1, or even 2 in the case of the Use Priority flag, avoids some freezing issues. Please see the comments in the EL-Connect script for how to appropriately test alternative values of the Use Priority and Use Suspend variables. The next flag, Dummy Mode, can be very useful. The eye tracker in your lab may not always be available, or you may find it more convenient to debug and test your experimental script on a computer that is not physically connected to the EyeLink host PC. If your script does not rely on real-time eye movement data, you can set the Dummy Mode flag to 1. This will open a simulated connection to the tracker, allowing the task to be run without having to comment out or remove all of the EyeLink integration code. The calibration sounds on variable simply ensures that the standard calibration beeps are played. To disable the beeps, simply set this value to 0. The following set mouse state equals true makes sure that the mouse cursor remains visible at this point in the task. getEDFName calls a function that is defined in the user script. It prompts the user to specify an EDF data file name that will be used to store the gaze data on the host PC. For compatibility with older versions of our hardware, the file name should not exceed 8 characters, not counting the EDF extension, and should only contain letters, numbers, and underscores. Note that you do not have to add the .edf extension at the end, as this is automatically added if left off. Once an EDF file name has been entered, the mouse cursor is made invisible. The next lines of code set the default calibration parameters. You can choose the background color, the foreground or target color, and the target size and the size of the central point. Please see the comments in this section of the script for a description of how the target size values work, and note that they have slightly different presentation based on whether you're using the with cam or no cam display method. If the useCustCal variable is set to 0, then the values set in the lines above will be used to draw the calibration targets. However, notice that in this script, the useCustCal variable is set to 1. This allows us to specify an image file to be used as a custom calibration target. If we set the variable to 2, we can use an animated calibration target in the form of an AVI file. These lines of code check whether a customized calibration target is being used, and provide the path to the relevant resource if this is the case. If 1 or 2 is used, please be sure that the path to the intended custom calibration file is set in the if clause immediately following the use custcal variable. The next if clause sets the thread priority based on the use priority variable value. When set to 0, the default, the thread priority simply remains set to high. This helps ensure optimal timing in the project by telling Windows not to interrupt with background tasks. If issues or freezing behavior is seen in the project, changing these values may help, as discussed in the comments on the main variables. Here, if the value is set to 1, we temporarily reduce the thread priority to aid in successful shifting of focus between the display handling methods. Most systems should not require this. Next, we set up a basic error handler and create the ELUtil and tracker objects. These lines of code should not be modified, as the rest of the code expects these variables to be set as they are in the example. The next if clause is an important one. If the dummy mode variable is the default value of 0, a connection to the host PC is opened by passing its IP address to the tracker.open function. Here we use the default 100.1.1.1 address. This should stay the same unless you have special hardware connection considerations, such as connecting to an EEG system. If dummy mode is enabled, by setting the dummy mode variable to 1, then a simulated connection is opened via the tracky.dummyopen function, allowing testing of basic project functionality without a tracker being physically present and connected. The next line of code actually opens an EyeLink data file on the host PC by passing the EDF filename variable to the tracker.openDataFile function. Here we create an attribute EDF namelog to make sure that the EDF filename is logged in the EDAT and text files that ePrime generates. This can be helpful in matching up EDF files with the relevant session if needed. The next line of code allows you to write some preamble text to the header of the EDF file, which can be useful at the analysis stage. The default is set to simply add recorded by ePrime project and then the project name. The code then uses the tracker.send command function to pass a string to the eye tracker containing the top left and bottom right pixel coordinates of the display screen. As a note, since the top left is position 00 instead of 11, the bottom right coordinates will be the resolution values -1. Many host PC settings can be changed directly via the host PC interface, but in some cases it can be useful to change these parameters via your experimental script. Here we set the calibration model to the 9-point or HV9 model. Next we write a message into the EDF file that contains the text display_coords and the same top left and bottom right pixel coordinates that we used earlier. This ensures that the gaze and stimuli will be displayed correctly in DataViewer, our analysis software. The monitor's refresh rate is also logged in the EDF file as a message. The following lines of code essentially ensure that all available event and sample data is both being stored in the EDF file and sent over the Ethernet link to the display PC. Different EyeLink eye trackers have different functionality with respect to what data is available at the sample level, so in order to configure the settings correctly, the script needs to know which eye tracker is connected. The code does this by querying the version number of the host software. These lines of code simply grab the version number and return the first character as an integer. All available event types are saved in the EDF file and made available over the link with these two commands. This code should not be altered. For the sample data, an if clause is used to check we are not trying to tell the host PC software to save or stream sample data that isn't available. Again, all available options are passed to the host PC via the tracker.send command function. As above, we strongly recommend that you do not alter these lines when you copy the code into your own project. This line of code allows a button box to be used to control the calibration and drift check process. Next, we clear the host PC recording backdrop in preparation for sending the backdrop image for the upcoming trial. Finally, we reset the thread priority to high if the initial settings needed to be changed earlier. To summarize, The EL-Connect script is where we make the initial connection between the ePrime project and the EyeLink hardware. Some variables can be modified in this code to change some specific tracker parameters on a project-by-project basis, including the calibration pattern to be used and whether to use custom targets. Having initialized a connection to the eye tracker and configured various host PC settings and parameters, the next integration step is to put the eye tracker into camera setup mode so that the experimenter can actually perform the camera setup actions, which include camera focus, adjusting thresholds, as well as the actual calibration and validation procedures themselves. Prior to entering camera setup, we have a simple text slide that lists the basic camera setup commands and shortcut keys. Actually entering camera setup mode is handled via a very simple inline script that calls the do camera setup function. The mouse cursor is then hidden in preparation for the upcoming experimental trials. After this, we enter a block level procedure. This is set to run a single instance of block proc, within which we have our task instructions, and then move immediately into the trial level procedure, which holds our 4 image presentation trials. Some of the trial-specific variables contained within trial list are later populated to the EyeLink data file output, which we will discuss later on. Before the next critical integration step, an inline code item, we have a simple text display slide called fixation. This uses a red plus as a central fixation point. This slide is automatically proceeded from and is merely there to ensure a fixation target is presented in an upcoming drift check without switching the graphics handling from the base ePrime items. We'll discuss this further when we get to the drift check line of the following inline code. When using EyeLink eye trackers, it is generally preferable to start and stop the recording at the trial level, rather than recording gaze continually throughout the entire experiment. The start recording inline script sends the appropriate commands to the eye tracker and also ensures that the trial stimulus is visible on the host PC screen. So let's go through this code in detail. First, we increment a trial counter variable and use the tracker.sendMessage function to send a special trial ID message to the EDF. This message will be used by DataViewer, our analysis software, to determine the onset of each trial. We then send a further message for DataViewer that clears its screen to a neutral grey background colour using the !V clear command. In general, any message that starts with !V will be a DataViewer integration message. The next lines of code provide the host PC with the recording status message to display for the current trial. These status messages can be a very useful way for the experimenter to keep track of the experiment's progress. The code simply constructs a string that comprises the word picture, followed by the image file name for the current trial, followed by the word trial and the current trial index. The next block of code determines what appears on the host PC screen during the actual recording. First, we put the tracker into offline mode, which it needs to be in order to receive the following commands. Then we clear the host PC recording screen and then use the tracker.bitmap to backdrop function to pass the image file name along with its dimensions and location to the host PC. The final lines of code in this block illustrate how to use drawing commands to add further markers or placeholders to the host PC recording screen. In addition to displaying images, the host PC can also draw primitive shapes such as lines, rectangles and crosses, as well as text. In this next section, we use the draw box command to draw a rectangle around the image. As we saw earlier, this rectangle represents the location of an interest area. The full range of supported drawing functions are listed in the commands.ini file on the host PC. The code simply determines the left, top, right and bottom coordinate of the rectangle and builds a string which passes those values as the first 4 parameters of the draw box command. The final parameter, 7, is the colour, in this case medium grey. It is important to note that this code is being executed before the trial recording has started and before any trial stimulus is shown to the participant. As we saw earlier, each trial starts with a drift check. This is a critical part of most eye tracking experiments as it allows the researcher to ensure that the eye tracker's calibration model is still accurate before any data is actually collected. A few seconds checking that the tracker is accurate before each trial starts can save days and weeks of frustration at the analysis stage. The drift check is handled by a single line of code which determines the drift check target type and location. The doDriftCheck function takes several parameters, which are described in detail in the comments. The first two are the XY location of the driftcheck target in screen pixel coordinates. The third parameter, draw, determines whether the driftcheck target is drawn using the default target specified in the user script or whether an E' object is used. The script illustrates how to use an E' object as the driftcheck target, so this parameter is set to false. The next parameter determines whether or not the escape key on the host PC can be used to trigger the camera setup mode. This can be very useful, particularly if the drift check fails, as you will need to recalibrate, so this parameter is set to true. The final parameter is only required if draw is set to false. It specifies the name of the E' object that handles the presentation of the target, in this case a simple red cross. This commented code illustrates the command to use if you want to use the default drift check target. Finally, we set the offline mode again to ensure proper transitioning between modes, and then start recording with a tracker.startRecording function. A short delay is added before the script moves on to allow the tracker to buffer some samples. This buffer is important as internal velocity calculations are based on a window of samples. The next two slides are simply telling E' to display our picture stimulus for the designated maximum duration, as listed in the trial list, or until a response key is pressed. Once that slide is finished, we display a blank slide, both to remove the trial image and to give us a timestamp to use to mark the end of the trial display. Note that using the onset of a blank screen instead of the termination time of the actual display node is based on E''s own recommendations for proper timer accuracy. The next item of EyeLink integration code is the stop recording object. The code starts by defining an offset value variable. As we will see later, this variable is critical in sending messages to the EDF file that accurately flag the onset times of critical trial events. The code here sends a message to the eye tracker recording the exact time that the picture slide screen was displayed. Since the screen was displayed some time ago, to get the correct time, we first take the current time in milliseconds and subtract the picture slide screen onset time as reported by E'. This difference is included in the message sent to the eye tracking data file as an offset value. Data Viewer will automatically subtract this offset value from the EDF timestamp of the message itself, so that the picture slide onset message will appear at the correct time in the data with the appropriate timestamp. If you do not use Data Viewer for your analysis, you can determine the actual onset time by subtracting the offset from the message timestamp. This section of the code illustrates some useful Data Viewer integration. The code allows the images that were shown during the recording to appear in the spatial overlay and animation playback views in Data Viewer at the analysis stage. As mentioned earlier, anytime you see a message being written to the EDF file that starts with !V, then this will be a message specific to Data Viewer. The message simply sends the !V image load center integration command and passes the image path, image location in pixel coordinates, and the image width and height. This allows Data Viewer to find the relevant image and present it in the correct location and with the same dimensions as it appeared to the participant during the recording. The next block of code illustrates how to define interest areas. The comments contain various examples, but in the uncommented active code, a single rectangular interest area is defined that matches the size and the location of the images by determining their left, top, right and bottom pixel coordinates. The message also contains an interest area index, 1, and an interest area label, image_IA. Here, the difference between the current time and the time the blank screen was shown is calculated, and the offset added to a blank screen onset message that gets written to the EDF. A further Data Viewer integration message is sent to make sure that it also displays a blank screen at the correct time during trial playback. Finally, after a short delay, the recording is stopped by calling the tracker.stopRecording function. The remaining code is further Data Viewer integration. The values of various trial variables are computed and sent as messages into the EDF that contain the !V trial var integration command, along with the variable label and variable value. These messages are what allow the variable data to appear in Data Viewer. This last trial result message is critical, as by default Data Viewer will use it to signal the end of the trial. Keeping the logged variables above the trial result message is important, as only items sent between the trial ID message and the trial result message will be associated with that trial by Data Viewer. After stop recording, we enter a break check trial inline script at the end of the trial procedure, which is followed by a similar break check block inline script at the end of the block procedure. These both hold the exact same code and serve as a way to gracefully exit the session early if needed, while still closing the tracker connection and transferring the EDF results from the host PC to the display PC. Once the trial and block procedures are complete, we show a simple goodbye screen and then proceed to the final inline code object, ELClose. ELClose is positioned at the end of the session procedure and handles closing the EDF file, transferring a copy of it to the display PC, and then closing the connection to the host PC in preparation for the end of the project. The command clear screen simply clears the tracker recording display to color 0, which is black. Next, tracker.setOffline mode puts the host PC into offline mode so we can transfer the EDF file. A brief delay is added to make sure that the tracker has had time to make the mode switch before tracker.closeDataFile is called to close the data file, and then receivedDataFile transfers a copy of the EDF file to the display PC. The if clause just makes sure the connection is still live and ensures we don't try to transfer an EDF file if we're running in dummy mode. For the receivedDataFile command itself, we simply pass the name of the EDF file and then the intended location of the files on the display PC. These two lines close the connection to the host PC. The final code is a simple error handler, which provides any relevant error messages should the project run into any issues. So, to summarise quickly, integrating ePrime and EyeLink eye trackers involves the following steps. Make sure that you have downloaded and installed the latest version of the EyeLink Developers Kit. Make sure that your ePrime scripts contain the following components. At the session level, the user script. This is critical as it contains functions and methods that are used by subsequent inline script objects. The ELConnect inline script that establishes the communication between your display PC and the host PC and allows you to configure various host PC parameters. The ELCamera setup script, which allows you to set up the participant and form calibration and validation. The trial loop should start with the start recording script and end with the stop recording inline script. For a comprehensive integration, use the stop recording code to make sure that key trial events are flagged and time-stamped appropriately in the EDF file by sending messages with the correct offset. If you're planning to use Data Viewer for analysis, then the stop recording script can also be used to pass trial variables and values, as well as commands that ensure Data Viewer uses the correct images and interest areas. Finally, use the ELClose inline script at the end of the session sequence to make sure that the connection to the host PC is closed and the EyeLink data file is transferred. I hope this video walkthrough was useful. Please do check the other ePrime templates, which illustrate further integration features, including how to read gaze events and samples over the link and use the data to control stimulus presentation. Finally, if you have any questions, please don't hesitate to get in touch with us, either via the support forum or by email.